Hey YouTube, welcome back to the SoftBoarders. Today we're going to be solving the problem of merge sorted arrays. The merge sorted arrays is basically given two arrays and the number of elements in each array. You want to merge array 2 into array 1. Given array 1 has extra filler space for the elements of array 2. Based on the information that we're given, we know since we have filler space at the back, maybe it might be a good idea to iterate these arrays from the back. So let's give that approach a try. We know the output of this is going to be another sorted array, but it combines two arrays. And the biggest hint is that they're both sorted. So if you're trying to combine two sorted arrays, we know the very last element is going to be the max of the two arrays. So if we think about the problem, we could have pointers to the last elements, and the last element of this array is just the 0, and this is going to be the placement. So you can call it the P. So this is where it's going to be placed. And we know the length of the second array, it's n equal to 3, and the length of the first array is m equal to 4. This is because there's 4 elements in it, the rest is just filler space. So we could just do the length of the entire array minus 3, and this will give us this index right here. So we could have another pointer right here. Let's call it I, and we can call a pointer at the end of this element as j. And now, if we just want to find the max of either one of them, and it would place it right here, that would, in theory, slowly sort the array. So let's try it out. So the max of 11 and 15, it's 15. So every time we find the max, we place it where P is pointing to. Move P down by 1, and we know we found it from 15, so 15 is sorted. So we can move J down by 1 as well. And then we continue the same thing over and over again. So max of 9 and max of 11, it is 11. So 11 goes to where P is pointing to. And then we move P back by 1 and I back by 1 because I was pointing to the 11 that we just inserted. And then we do the same thing. What's the max of 9 and 7? It's 9. So 9 goes to where P is pointing to. And the J moves back. And now after J is at 7, we look at max of I and J. We know it's a 7. So let's assume it's the J, the 7 from the J that we're taking. So P is pointing, oh actually, my bad, I forgot to move the P. The P should be pointing, oops. The P should be pointing to where the 11 is. So when we find the max of 7 and 7, we find a 7. So we place the 7 right there. And as soon as a case like this happens where J is at the last element and we insert the last element, so J is less than 0 in the index, we know that these are two sorted arrays and we're trying to find the max. If we exhausted all the options in the second array, that means all the items remaining in the first array are actually smaller because we're getting the max. Are already smaller than the items that we just sorted to the right. So if we can clearly see that we just merged array 2 into array 1. And the runtime for this was just O of m plus n, because if this is array m, we went through most of it, and we went through all of n, or whichever is smaller. The runtime of this algorithm is actually not O of m plus n, it's just O of m or n depending on which one's bigger. So basically at the end of it, you know which one's bigger and you just merge it in, and you know it's a sorted array. So let's try to code this out. Alright, for now, let's go through the code walkthrough of the solution. So we do exactly what as we discussed in the algorithm that I just described. and we set the positions first. P is going to be where we place the elements. So P is going to be the length of array 1 minus 1 because it's zero-based indexing, so it's right there. J is going to be the last element of array 2, so it's length of array 2 minus 1. And I is going to be the first actual element of array 1, so it'll be the length of array 1 subtracted by the length of array 2, so you can go back, and then minus 1 for the zero-based indexing. So you know it's right here. And then the condition is this: while j is greater than or equal to 0, or I is greater than or equal to 0. This means as long as j or I are still within bounds of their array and it hasn't surpassed or haven't gone past the last element to the left. And the condition is basically this: we try to find the max. So is I greater than j? If it is, then we set array 1 we set the position, which is right here, to be equal to the max element. So this is what the if else case takes care of. One of the cases I think I forgot to mention is at the end is, what if I terminates faster? By that I mean if I is no longer greater than or equal to 0. That means all the elements to the that are left in J are smaller than all the elements of I that we've already went over. So if you in this algorithm, we always place the max element. So we have to check to see if there are some elements in J left over. Because if they are, they haven't been merged into array 1. And we know everything else to the right of it is already sorted and it's greater than all the elements of J. So in the end, we just have to check the case if J is still greater than or equal to 0. And if it is, then we set for each item the position of array 1. We set it to array J and we decrement J and P till we get to the end and J is no longer greater than or equal to 0. And at which point we can return 1. I'll let you guys take a closer look at it. If you guys have any questions, put it in the comments section. So now, if you want to think about the runtime and space-time complexity, we notice that if our I values, the last element of the I, or the first element of the I, is actually greater than the elements of J, then we go through every single element of I, and then we add all the elements of J. So the runtime for this would be O of m plus n, because in most cases, if you run out of i's before j, would have to go through all the j's first, just as well. And for our space complexity, we are actually just merging the second array into the first array in place. So we're not actually creating extra variables, extra storage, except for the variables, and the variables are just constant. So our space-time complexity for this solution is actually just O of 1. Alright, YouTube, thanks for watching. If you have any questions, leave it in the comments below. Thank you.